Okay, everybody, we're going to get started. So welcome again to the University of Washington's Astrobiology Colloquium. Today, I am delighted to introduce Dr. Rachel Osten from the Space Telescope Science Institute and the Johns Hopkins University. Rachel is an astronomer. She did her undergraduate degree at Harvard University and her PhD at the University of Colorado, Boulder. From there, she went on to be both a Jansky Fellow and a Hubble Fellow. She's currently an associate astronomer at the Space Telescope Science Institute, where she has served as both the deputy project scientist for the James Webb Space Telescope and as the deputy mission head for the Hubble Space Telescope. So I'm delighted to introduce her today to talk about the space weather environment that stars create.
All right, thank you very much. Can everyone hear me? Yeah, okay. I'm gonna try to anchor that to my sweater so my scarf doesn't drag the mic down. So thanks very much for the invitation. I'm really happy to come and talk to you about this topic. As Vicki mentioned, I'm a stellar astronomer, so that's going to be my particular slant talking to you. And I'm going to try to make sure that this is interdisciplinary. My research actually is fairly interdisciplinary between looking at the sun, looking at stars, and then thinking about the impact of what we see on these stars and what that might mean for planets around stars. So just very briefly show some of my current collaborators or recent collaborators. I'll be showing some work from my now former PhD student, Michael Crossley, and some current and new collaborators as well. All right. So to start off, this is pretty obvious, but we're in the age of exoplanets, right? It's been 20 years now since the first planet was found orbiting a star outside of our solar system. I had to update this today because I had this graphic in a talk I gave a couple months ago, and there's a different number of exoplanets discovered even back then, a couple months ago. And this is an artist's impression of that very thin, tenuous atmosphere that a planet has with the star featured right in back of it. That's going to be the central theme of my talk, trying to understand stars so that we can understand the exoplanets. And in the ensuing time since the first exoplanets were discovered, there's been a fantastic intersection of stellar astronomy and exoplanet science. And this takes place in a couple of different manners. The first one is a very basic approach that since pretty much all of the exoplanets we found outside of the solar system, we found around other stars. You need to understand the stars in order to find the exoplanets. And this is just a summary of some of the different observational techniques that we have in our toolbox to find exoplanets. Astrometry, direct imaging, radial velocity, the transit method, microlensing method, all of those rely on some mechanism that involves the star and looking at a wobble around the star or a dip in the star's brightness. But in order to interpret those signals and find the exoplanets, you have to have an understanding of some of the fundamental properties of the star. So that's one nice intersection between stellar astronomy and exoplanet science. The next point of intersection is in characterizing the exoplanets. This is what a spectrum of an Earth-like planet might look like. And there's a bunch of different features here that are being produced by the processes on the planet. However, you've got radiation incident on the planet from the star, and you need to take that into account for coming up with your potential biomarkers or biosignatures that you can use to point out whether the signature in your spectrum is coming from the planet or is induced or influenced by the star. And then finally, the intersection of stellar astronomy and exoplanet science comes in understanding the environment, or the ecosystem, if you will, in which those planets are existing. And this is a schematic showing the sun. This is not to scale. Here is the Earth in its magnetic bubble, its magnetosphere that protects it from the influence of the magnetic field of our star, the sun, and the magnetic activity that the sun creates. And so one of the one of the central underlying themes to the work that I'm going to be talking to you about today centers on this fact that we really need to understand stars as an essential component of trying to answer this question, are we alone? That astronomers, astrobiologists are all really excited about doing. The public is really excited about this. We have the prospect in the next, maybe in the next several decades, of trying to answer this question. And so my thesis is that we need to understand stars if we want to make progress in that. And that's been identified in NASA astrobiology roadmaps and whatnot. But as a stellar astronomer, that's the part that I try to emphasize. One component of that I showed you previously in understanding the environment in which exoplanets find themselves is this topic of space weather. And that comes about because we live around a magnetic star. We have a very technological society. We have satellites. We're reliant on spacecraft communications, and that means that we're susceptible to anything that the sun can do. Things like solar flares, coronal mass ejections, the solar wind. This is all a component of what we call space weather in the Earth's perspective or the solar system perspective. But that's something that we can think about in an extrasolar planetary perspective as well. And space weather with the knob turned up to 11 or maybe 1,000 in the case of some of the stars I'm going to talk to you about today is a habitability concern. So when we talk about space weather, we talk about solar eruptive events. And there's three parts, and this is going to be important when we start to think about what the stellar counterparts of these events might be. And there's the sort of familiar solar flare. This is a movie of the sun's corona. And you can see these coronal loops. These are arch-like structures. They're very dynamic. Those are electrons that are tracing out magnetic field lines, and you can see that those field lines are moving around, interacting and reconnecting, brightening, and that's structures that produce solar flares. There's two other parts to a solar eruptive event, and that's shown in this movie. This is the same event. If you can read the date, this is something that happened in 2012, January. So this is very close to the surface where the coronal radiation, the extreme ultraviolet and X-ray radiation is coming from. What you're seeing in this movie, which is looping over and over again, is structures that are much farther away from the sun. This white circle here indicates this diameter of the visible portion of the sun. So you can see in the very beginning there's a loop-like structure here that explodes. We're looking at size scales of multiple solar radii. This is an expulsion of mass from the corona that starts way down here and propagates out into interplanetary space. That's the coronal mass ejection. And the fuzz that you can see at the very end, it's not fuzz, that's actually signal. Those are energetic particles that have energies of several hundred MeV to maybe even up to a few GeV hitting the detector. This is a movie that's made from the Solar and Heliospheric Observatory that sits between the Earth and the sun, always watching the sun, watching out for events like this. So when it comes to the solar system and space weather in our solar system, the so-called geoaffective parts of these eruptive events are actually the last two that I mentioned, the coronal mass ejection and the energetic particles. And this is a schematic that just shows you that it's not just that they are happening, but location, as in real estate. It's location, location, location. So where the event happens on the surface of the sun and where the Earth is in its orbit around the sun are key determinants to whether there's going to be a major space weather impact. And NASA has a fleet of spacecraft around different planets in the solar system and different orbits around the Earth, and it has a very sophisticated fleet of modelers who are looking at what the sun is doing and trying to predict what the chances are that one of these major events might happen, and then determining through looking at these magnetic field lines from the sun, predicting what spacecraft might need to take cover to protect themselves. So there's two, if I could summarize the entire talk, and if you want to fall asleep after the slide, go right ahead and I'll wake you up at the end. The two key questions that this research is trying to address are exploiting what's called the solar-stellar connection, but for an understanding of space weather. So on the one hand, we have a star that's 1 AU from us that is very well characterized. We can study it in detail. We know about its magnetic activity, its wind, flares, coronal mass ejections, energetic particles, et cetera. What information can we use from that detailed body of knowledge to understand space weather outside the solar system, or what we call exo-space weather? And similarly, we have one star that we can study in incredible detail. On the other hand, we have, as Carl Sagan said, billions of stars in our galaxy that represent a variety of different evolutionary pathways, masses, radii, ages. So what information can we learn about the sun, in particular its past and potentially its future, by looking at these studies of other stars? So exospace weather and exoplanet habitability critically depend on stellar magnetic fields and these eruptive events. I've got sort of the next couple slides have the same text down at the bottom with a couple different examples here. The point is that the star's magnetic field, as I showed you in some of those graphics before, creates an ecosystem that helps to set the environment that planets and life experience. And it's a crucial component of understanding the experience that a planet has. Stellar magnetospheres can influence the inner edge of the traditional habitable zone. And as I mentioned before, it's the coronal mass ejections and proton events that have the biggest impact in determining the effect on planetary atmospheres. That's also exactly the region where we have the fewest observational constraints from the stellar perspective. So in our solar system, we see that coronal mass ejections had a significant impact on Mars and its evolution. The MAVEN mission to Mars was one of its prime purposes was trying to investigate this. What is the history of atmosphere loss and water loss on Mars, and how is that influenced by coronal mass ejections from the sun? We don't have quite as nice graphics for other planets outside the solar system, but this is a schematic just showing for a planet around a star that has a very high flaring rate and a high rate of coronal mass ejections, that coronal mass ejections act like an enhanced stellar wind and can compress the magnetosphere of the planet and expose the atmosphere to ionizing radiation from the star. So that's an additional atmospheric loss mechanism that needs to be taken into account potentially for these exoplanets. And finally, the influence of the particles can be severe. So this is a paper that's an addition to a famous paper from about 8 years ago, showing the influence of the energetic particles on the atmosphere of an exoplanet, an Earth-like exoplanet around an M-dwarf. And if you have only the electromagnetic radiation from the flare, there's not a significant impact on the ozone column depth during this flare. However, if you add in protons, scaling from the relations that we have established for the sun, there's a very significant impact. This exoplanet loses all of its ozone over timescales of months to a year, and it takes several decades. This is log time, right? So there's pi times 10 to the 7 seconds in a year. So it can take several decades for this exoplanet's atmosphere to recover the ozone, all due to whether, all depending on whether there are protons in this flaring event or not. So there's the importance of being magnetic. This is, I have to apologize, I tried not to have a huge amount of jargony related graphics, but this is one of those confusograms. So this shows complexities to large scale stellar magnetic fields. So you've got stellar mass on the y-axis and rotation period on the x-axis. So the size of the symbol tells you about the energy density. So larger symbols have, those stars have a higher energy density. The color refers to the overall shape of the magnetic configuration. Blue is poloidal and red is toroidal, and I may have flipped that. And then the number of points on each symbol tells you how axisymmetric the magnetic configuration is. So if it's big and if it's very almost circular, that's a very axisymmetric magnetic configuration. If it looks like a star, it's very non-axisymmetric. So for these low mass stars, the M dwarfs, you can see they have a very high energy density. They have mostly poloidal magnetic fields, and there is a variety of different magnetic configurations, largely axisymmetric, but some stars having a very strong degree of non-axisymmetric. Why is that? That's related to the dynamo generation of magnetic fields that's taking place in the interior of the star. And an important point to point out is that when you look at a star, it's not, at this point at least, our understanding of stellar magnetism is such that we can't actually predict this with very fine scale based on the other fundamental properties of the star. So this was an excellent comparison case. These are two stars that have nearly the same temperature, they have nearly the same mass, nearly the same radius, nearly the same rotation period. Metallicity is very similar. When you look at these two stars and you look at the integrated evidence for magnetic fields, you see they both are indicating very strong field strengths. And yet when you look at that structure, the large-scale structure of the magnetic fields, there's something very different. One shows a very complex, non-axisymmetric shape, and the other one looks like a dipole magnetic field that's slightly axisymmetric. So these stellar twins are not necessarily coronal twins or magnetic twins. Okay. So I said that there's three components to these eruptive events. I'm going to talk about the coronal mass ejections and eruptive events, but first let me talk about flares. The first point I want to make here is that observing flares on stars is easy. It's in quotes. I've organized multi-wavelength flare campaigns, and it takes a lot of work writing proposals and getting telescopes to track stars. But the point is that there are different observational signatures across the electromagnetic spectrum, from the radio through to the optical, into the ultraviolet, soft X-ray, and even further into the X-ray. And when you look at solar flares on the sun, there's a check mark in every single row here. That's sort of by design. I mean, I made the table that way. But what is remarkable is that when you look across different types of stars, you see a check mark in pretty much every single row as well for other stars. And so that's really a good confirmation that we're looking at the same physical processes in these stars. And it tells us that there's a ubiquitous mechanism that's taking place on these stars as it is on the sun. And that when you look in these different wavelength regions, you're probing different layers of the stellar atmosphere. You're looking at different physical processes. You're looking at particle acceleration. You're looking at plasma heating. And so you're able to make interrelationships in these different atmospheric layers and across stars of different types. So when you look at the flares and look at the radiative energy partitions, there is a striking similarity between solar and stellar flares. And this is a table just comparing some of the dominant forms to some of the dominant flare signatures coronal flare signatures, and this hot black body that shows up at blue and optical wavelengths. That's been very well studied by some members of the astronomy department here. One thing that's striking is that if you look across on active stars on the sun, you see that the energy fractionation in these flares is very similar between solar flares and active stars. So that's good. That is another confirmation that we're looking at the same basic physical process when it comes to the radiative energy in the flare. However, and there's a question mark here because this is an active area of investigation, there's some evidence now that we might be seeing dissimilar accelerated particle characteristics. When you look at the population of accelerated particles near the surface of the star, I apologize, this figure got a little washed out. Radio observations are great for diagnosing accelerated particles. When you look at radio flares on stars, you're seeing gyrosynchrotron radiation, and that's coming from electrons that are mildly relativistic. They're spiraling in the presence of magnetic fields. The radio emission is changing with time as the characteristics of that particle acceleration are changing. When you look at solar eruptive events, there's roughly equal amounts of energy in the accelerated particles and in the bolometric radiated energy. So if you account for the fact that a flare is radiating across the electromagnetic spectrum in those different components that I showed you in the table, and sum those up, you get roughly equal amounts of energy in the accelerated particles and the bolometric flare energy. Some studies of M-dwarf flares are suggesting that there's more energy in the non-thermal particles for these flares than in the coronal emission. And relative to the flare X-ray emission, stellar flares appear to produce larger radio amplitudes than for solar flares. So another indication that there might be a difference in the accelerated particle characteristics of stellar flares compared to solar flares. This is work that my colleague Adam Kowalski, a former student from this department, has been investigating using radiative hydrodynamic models of stellar flares in the blue and optical. And this has been a point of contention for quite a while, that if you take a solar-like prescription for an electron beam in a flare and stick it in a stellar atmosphere, you could not reproduce the observed stellar flare. If you did the same experiment for a solar flare in a solar atmosphere, you could reproduce the observed solar flare signature. And so that just indicated that something was off. The experiments that Adam has been doing have shown that by increasing the beam flux, the amount of energy in the electron beam, by up to 2 orders of magnitude, you can reproduce the observed stellar flare signature. More recently, he's been fiddling with the prescription for the electron beam. And so this is an active area of investigation, I would say, but it's hinting that there might be a difference between flares in terms of how the particles are accelerated, where if you look at the radiated energy, there seems to be a good agreement with solar flares. I want to briefly tell you about this very unique set of observations that come to us via a sort of unexpected route. And that is using a satellite that was designed to study gamma-ray bursts that is telling us about a very extreme and rare population of stellar flares. So the SWIFT satellite triggers on transient sources of hard X-ray radiation. That's what gamma-ray bursts are. They're the death throes of dying stars at the edge of the universe. They give off bursts of hard X-ray radiation or gamma rays. The SWIFT telescope can sense a large portion of the sky at any one time. It senses these bursts, and then it can very swiftly reorient the satellite to pick up afterglow radiation at soft X-ray, UV, and optical wavelengths. Those turn out, you remember that table I showed you of stellar flare observational signatures? You see the same kinds of signatures in stellar flares. And so SWIFT has, in the 10 plus years that it's been up in space, has seen about a dozen very bright, very rare stellar flares. And these are probing the extreme ends of stellar flares. So with energies that are among the most energetic flares ever seen on different kinds of stars. This one particular flare observed on the nearby M dwarf EV-LAC, which I like to tell people this was a gamma-ray burst that was 17 light years away from us, which is pretty impressive. This particular flare on EV-LAC, the X-ray luminosity of the flare exceeded the bolometric luminosity of the star. So to put that another way, the bolometric luminosity of the star increased by factors of several on timescales of 10 minutes. And that's something that you think about changing on evolutionary timescales, billions of years, not something that you can check with your watch. Similarly, another event on another nearby M dwarf produced temperatures in its corona that are typically only seen in the deep interior of a star, temperatures up to 300 million degrees. So they're very extreme. We would not see these types of events on the sun. And when you look at these very extreme stellar flares, this also gives us a hint that there might be a change in the amount of hot plasma that's being created. Now, there's a scaling relation that's shown here between the flare peak temperature and the, what's called the peak emission measure. That's the amount of material that's involved in the flare. For solar flares, there's a nice power law relationship here. And for a sort of heterogeneous collection of stellar flares, there's the same scale. But these very energetic flares, it looks like instead of the power law increasing, which would indicate that you have a significant amount of hot plasma being created, it looks like this is flattening. So why that is still to be understood. But these very extreme flares are probing regions of parameter space that we wouldn't have with other types of flare observations. And this is a slide that I just wanted to show because I'm talking to astrobiologists. Some of you may have participated in studies looking at stellar flares as astrophysical input to the impact on planets. And the Great Flare of 80 Leo, which Suzanne Hawley published several years ago, gets a lot of love. I just want to point out that there's a diversity of different kinds of flares. This one's great, because some of these are even super. There is no one particular stellar flare that it has comprehensive wavelength coverage from optical to UV to X-ray that's really needed to do the detailed astrobiological inputs. But there are flares that are larger. There are flares that have more different types of observational constraints from the astrophysical perspective. And so for those of you for whom this might be interesting, I just want to make sure you know that there's a diversity. Diversity is good. Okay. So I talked about in the beginning about how important it was for coronal mass ejections and energetic particles for understanding space weather. And then I told you that it was really easy to observe flares. So now I want to talk about trying to observe coronal mass ejections on other stars. And the title here is sort of the punchline. Observing CMEs on stars is hard. Part of the reason for that is because of what I said before, that observing flares on stars is easy, right? Pick a region of the electromagnetic spectrum and you're going to see a signature of a flare. This is a list of some of the observational signatures of coronal mass that have been used to study coronal mass ejections. Same format as before. Here's the sun. There's a tick mark in pretty much every row. And then you'll notice there's a difference here, that in the stars column, there's question marks where this observational signature has been tried. There's a big X, big old X in the top one for Thomson scattering. The characteristics of these coronal mass ejections, the size scales that you're talking about, just a few stellar radii from the surface of the sun, of the star. The brightness contrast, which starts at 10 to the minus 8, 10 to the minus 9, and you're looking at something that's evolving in time. It's not a point source. This is just out of the range of possibility for astronomical coronagraphs right now. So there's a big X there. But there's question marks in many of these other techniques. And there have been papers published before that have claimed to see coronal mass ejections, stellar coronal mass ejections. But typically, they are interpretations of what I call weird flares, right? Which is interesting, right? Not all flares behave the same way. We don't expect them to behave exactly the same way. However, if you want to truly learn about the astrophysics of coronal mass ejections on stars, you need an observational technique that you can use as a systematic probe of CMEs and not relying on weird flares. So what I'm going to talk about for the rest of the talk is sort of two of these. One is looking at an association with stellar flares and seeing what we can learn from that avenue. And then this observational signature called the type 2 burst, which I'll explain in a little bit more. So in essence, we want to extend the solar-stellar connection to flares and CMEs. Let's see. So I like to picture this as a little rectangle. You've got the sun, its flares and CMEs up here. There's very definite relationships, scaling relationships between the flares and CMEs. On the sun, there's solar and stellar flare relationships, which I talked to you about a little bit earlier. You've got 4 orders of magnitude difference in energy between the largest solar flares and the largest stellar flares. And what we really want to do is see if we can fill in the lower right corner of this rectangle to see if there's a relationship that we can come up between solar and stellar CMEs, and then between stellar flares and stellar CMEs. And this is sort of a cautionary note that the first solar flare was detected in 1859. The routine detection of solar CMEs didn't happen until 1971. That was 110-ish years later. The first stellar flares were detected in the early 20s, and we don't know when we'll have routine detections of stellar CMEs. That's sort of the point of some of the recent research. So going into these scaling laws are nice. There's a lot of data on the sun. We can look at empirical correlations. There's 2 recent papers, one by Alicia Arnio, another by Jeremy Drake and his colleagues, that have looked at solar flares and solar coronal mass ejections. And both approaches find a relationship between the mass in the CME and the energy in the flare with roughly similar index to the relationship. And if you look at equipartition, which I talked about earlier, in the sense of the energetic particles and bolometric flare energies, if you look at the energies in the CME and the energy in solar flares, there are a couple of different studies that point to the same direction, that the energy in the CME is roughly equivalent to the total bolometric energy in the flare when you account for the fact that flares produce radiation in different parts of the electromagnetic spectrum. And so this is something that I did with my collaborator Scott Wolk a few years ago. We looked at some of these relationships and then asked, well, what happens if we take that assumption that you've got an equipartition between flare energy and CME kinetic energy, and apply that to stars for which we have counted the number of flares that are occurring, and use that to infer what an implied rate of transient mass loss might be. So and this is where that table that I showed you earlier on energy partition, that was actually a nice byproduct of this piece of work. So in order to be able to relate the flare frequency distribution, the number of flares occurring as a function of flare energy, and to be able to put flares observed in different parts of the electromagnetic spectrum on the same footing, you had to have some understanding of the energy fractionation. So if you do that, and you do that, this is an example of the same star with flares observed at optical wavelengths and flares observed at X-ray wavelengths. They have a very similar distribution. The flares themselves cover different ranges of energy, but when you account for the fact that, that there's a different amount of energy coming out in each portion of the wavelength, and you integrate up all of these flares, you get a very consistent implied cumulative mass loss rate, which is very high. 10 to the minus 11 solar masses per year is about 3 orders of magnitude higher than the sun's present day mass loss. And it is also inconsistent with the one indirect method we have for detecting mass loss from stars. So there's one interesting result that suggests that maybe applying these scalings on stars in a one-to-one fashion, as we've done for the sun, might not work. So then this gave rise to a question that my former graduate student spent the last couple of years trying to answer, and that is, does a high flaring rate give rise to a high rate of coronal mass ejections? So this is a very opportune time to ask this question for a couple of reasons. One is that there's new generations of low-frequency radio telescopes, the low-frequency array in Europe, shown on the left, the upgraded Jansky Very Large Array on the right. There's also the Murchison Wide Field Array in Australia, which has come online in the last several years. These radio telescopes have much increased sensitivity compared to previous generations of radio telescopes. They can access a larger part of the frequency range at a given time. And so, if the instrumental capabilities were favorable for doing this kind of a project, there is an interest on the part of the astronomy and exoplanet community on trying to understand what impact these other components of an eruptive event on stars might have for planets. And so that's actually how I was able to fund this proposal through the NSF, by selling it on a habitability perspective. And we're looking for something called a type 2 burst. I'll go into what that is in the next slide. But we're looking for a signature that is associated with the CME itself and not the flare. So we had what we thought was a promising tool to explore the systematic behavior of stellar CMEs. So let me run through briefly just what we expected to see. I'll show you what we saw. So if a flare occurs, we're assuming that a coronal mass ejection is going to happen with it. This is an association plot for solar flares, and just showing that for very energetic solar flares, you almost always have a coronal mass ejection. The most energetic coronal mass ejections are traveling through the atmosphere of the star very quickly. If they exceed the local Alfvén speed, they can drive a shock. And this is a plot just showing the distribution of CME speeds. Some of the fastest ones are traveling in excess of several thousand kilometers per second. And they produce an MHD shock. The atmosphere of the star is getting less dense as you go further and further away from the surface of the star. That MHD shock is exciting plasma emission as it's traveling outward. And the signal, so as the density is decreasing, plasma emission traces electron density. So the frequency is changing with time. And that produces a very characteristic signal shape in frequency and time that you can predict if you have an understanding of the atmosphere of the star, if you know what the atmospheric scale height is, and the observables. The observables are the frequency drift rate, which you can constrain from the observations, the frequency, which is another observable, and then the only other free parameter is this exciter speed. So that's how fast the CME is traveling through the atmosphere. And this is an example of one of these type 2 bursts on the sun. You can see it's got a very nice signature here in frequency and time. It's actually showing harmonic structure, so you've got fundamental and harmonic emission. But again, you can reproduce what the expected shape is based on the speed of the CME and the atmosphere that it's traveling through. So we designed an experiment to try to constrain this using some stellar observations. We targeted stars with high flaring rates to test that close association. We wanted nearby stars. We needed to have constraints on the coronal temperature and electron density so that we could do that atmospheric modeling. We wanted stars that had magnetic field measurements in their photosphere so that we could do some at least simple-minded modeling of the Alfvén speed of the star, and previous evidence of radio bursts so that we knew that something had happened on this star in the past. And these results have now all been published. So because we were using a slightly different perspective than what solar physicists use, in that table of observational signatures for CME studies, the Thomson scattering via coronagraphic measurements that are used for solar measurements, and that's the movie that I showed you at the very beginning. That's the workhorse that solar physicists use. So even though they have all those other tools at their disposal, they mainly concentrate on using the coronagraphic difference imaging movies. But we don't have that luxury, so we have to use some of these other techniques, and we wanted to have a way to determine if what the information we were extracting from our stellar data was actually going to be reliable in terms of the parameters we're trying to constrain. So we had a set of solar data that we could use as a sort of test particle, where we had solar type 2 data, we had X-ray flares from the sun, and so we could, pretend that the sun is a star and do this experiment, see what answers we got, but then we could sort of lift the lid, if you will, and see what the right answer is by looking at those coronagraphic measurements and then see how well we were doing. So the upshot is that you can determine CME velocities, good to about a factor of 2, which is pretty good. Masses to an order of magnitude, and then kinetic energies, since it depends on the product of those two, is determined slightly worse, but this is pretty good. So then we went out, or Michael went out and analyzed a lot of data. In total, I think he analyzed over 80 hours of radio observations, which was quite a feat for just a couple of years worth of effort. And what I'm showing you here are the dynamic spectra of, it doesn't look exactly like the solar dynamic spectra I showed you before. And these are light curves where we had some simultaneous optical observations. We saw some flares. Now this is time on the x-axis and frequency on the y-axis. And the color scale shows you the flux density. This is the real component of the visibilities, and this is the imaginary component of the visibilities. And I can explain this a little bit more, but we're taking advantage of the fact that light is a wave. So when you observe a wave, you have an amplitude and a phase. You do Fourier transforms, and you end up with real and imaginary components of that visibility. We've got total intensity on the top, and then circularly polarized intensity in the middle. So basically, the imaginary plot is our test. If there is a signal that's real, that's coming from the star, it should show up in the real component and not in the imaginary component. Now, if you're listening to me and you're squinting at this plot and you're thinking, it doesn't look like that plot you showed me before with that nice structure, drifting, and frequency and time, don't worry, we didn't actually see anything. Your eyes are fine. We didn't see any features identifiable as type 2 bursts. We didn't really see any features, period. We went back on an additional 44 hours of radio-only measurements. This time we did see something. So here's a burst. There it is in the real component, and it's absent in the imaginary component. There's some polarization to it. However, one of the strengths of using this observational technique is that we can predict what the shape of the signal should look like based on our understanding of the atmosphere of the star. And the features of these bursts, namely the amount of frequency space that the burst traveled through, how fast it did that, the duration, are not consistent with what we expect from a type 2 burst. So we didn't see any type 2 bursts. So I'll be honest, right? We didn't see anything. Why didn't we see something? This is what distinguishes a real scientist, right? So why didn't we see anything? Is it because we were unlucky? Is it because there was just a mismatch between the parameters of these type 2 bursts and our observing sensitivity, even though we've been getting better at increasing the radio sensitivity of our radio telescopes? This is a plot that shows the size of the CME on the x-axis and its brightness temperature on the y-axis. And the region of parameter space that we're sensitive to as a function of frequency is shown in the shaded triangle, and it's different for each frequency. So we're sort of marching from the top left to the top right to the lower left. The dotted line here is the maximum brightness temperature that we've seen in solar type 2 bursts. Now, when we've seen stellar radio bursts before, we've actually gone all the way up to this upper bar. So this is not necessarily a limiting factor. These are the regions where those bursts that we did identify that were much lower significance than the assumptions that I'm making over here. So that's why they sort of stick out over here. And from some of the modeling that Michael did of how this CME might be evolving in time and the frequencies that we're using to observe, we can constrain the maximal area that we might have been sensitive to. And so, yeah, it's possible that they're just, the type 2 bursts might be happening, but they're an extremely small fraction of the size of the star. Another possibility is that these CMEs are occurring, but they're not very fast. Right? On the sun, we think that these very CMEs that have a lot of kinetic energy can do so because they have a huge amount of mass or because they're traveling very fast. So we could do some admittedly simplistic, but modeling of what the alphane speed in the outer surface above the star might look like. So this is speed as a function of distance. These horizontal lines are the speed that we would interpret using some of the scaling laws from the flares that we observed on this star. And then this shaded area is that factor of 2 padding that we gave ourselves from the solar flare study. And then this is based on, these are for the stars that we observed using the frequencies that we observed. So this suggests that the alphane speed might be larger than the speeds that we would infer. So maybe the alphane, maybe these CMEs are just not super alphanic. And then finally, we have the possibility that we're having flares, but no coronal mass ejections. And remember when I told you earlier about that relationship between flares and CMEs implies a very high rate of cumulative mass loss that appears to be inconsistent with observations of weak stellar winds. So there's a couple of ways to slice and dice it, but the final result is we didn't see any type 2 bursts. We expected to see many, either several tens if flares and CMEs are happening in a 1-to-1 relationship like they are on the sun. Even if you only expect a flare to happen every time there's a super alphanic event, we still should have seen a couple of type 2 bursts, and we didn't. All right, so we're left with this question of whether stars can produce eruptive events, and then whether we can observe the CMEs. So we're sort of back to square one. I can go back to that observational signature table and maybe put an X next to the type 2 bursts. But it's more complicated than just taking the sun and scaling it to an M dwarf in terms of its flares and CMEs. So future work in some of these areas that I pointed out is looking at the nature of accelerated particles. looking at the differences between solar events. We need to look to other potential CME signatures to make more progress in this area. And then appeal to modelers, solar and stellar flare modelers, to try to understand when and how breakout might occur. So I know I've been talking for about 50 minutes. I don't want to talk for a huge amount longer, but there are two quick things I want to talk to you about, because I've been actually doing a lot of future science in addition to telling you about things that I haven't seen or my graduate student hasn't seen. One's on the radio end and one's on the Xray end. So I'm a member of a science advisory council for something called the Next Generation Very Large Array. This is a sort of successor to the current very successful Jansky VLA. The idea for this telescope is to utilize the advantages of being in New Mexico. I think of this as filling the state of New Mexico with radio dishes. So increase the sensitivity beyond, about 10 times beyond what the VLA and ALMA can do. Increase the resolution and utilize a frequency range that's sort of intermediate between what the VLA can do and what ALMA can do. In the context of this current talk and looking at exospace weather, this isn't something I've emphasized in the previous part of the talk, but trying to directly constrain stellar winds, that's an important counterpart to looking at these transient stellar wind, which is the coronal mass ejections. But you can detect or constrain radio emission from an ionized stellar wind by looking at this frequency range above 10 gigahertz. There's a couple of important applications here. One is by looking at solar analogs and trying to understand what the sun's mass loss history may have been by looking at solar analogs of different ages. We would be able to make improvements by about 2 orders of magnitude compared to current constraints. We would be able to survey basically all of the M dwarfs within 10 parsecs and put very significant either detections or constraints on their stellar winds. And we've got one upper limit on the wind from Proxima. We'd be able to get below that for the very nearest M dwarfs. And then these 2 circles, those are the astrospheric method that's been used to infer stellar winds. And I can go into a little bit more of the differences between direct and indirect methods, but we need to have a more sensitive direct method for detecting stellar winds. And then finally, I'm also on the STDT for the Lynx X-ray mission concept, which is one of the 4 large mission concepts that NASA is studying for the next astrophysics decadal. And you can think of this mission concept as sort of like a super Chandra, 50 to 100 times the sensitivity of the current Chandra, with angular resolution and spectral resolution that are not going to be seen after the Chandra mission ends. So Europeans are planning a high-energy mission called Athena. It's not going to have the kind of angular resolution or spectral resolution that Lynx would be able to provide if it were an approved concept. And in the context of habitability and exospace weather and thinking about the impact of stellar activity on the habitability of exoplanets, there's a number of different questions that X-ray observations are particularly attuned in addressing. And they range from understanding where planets form when they're very young, understanding the physics of young stars and their accretion and flaring, magnetic reconnection flares, looking at the characteristics of flares on different types of stars, stellar winds, including potentially a few more observational constraints on coronal mass ejections. And then this series of plots over here is just a teaser for showing the influence of the star's X-ray emission and its evolution in time. So these are calculations that Colin Johnstone did for a grid of different planet masses and different initial atmospheric masses of an exoplanet atmosphere for an Earth-like atmosphere. And depending on the rotational evolution of the star at different phases, at 100 million years or a billion years, doesn't take one single path between those two ages. And depending on exactly what the evolution is, that can determine whether the planet loses its atmosphere or keeps its atmosphere. So it's important to understand that influence of the star on exoplanets. Okay, so I'll end where I started with the space weather environment that stars create. It depends on coronal mass ejections and energetic particles. These are the least constrained observationally from a stellar perspective. They're the most interesting. The current tools that we have mostly involve scaling up from solar relations. And while that gets you somewhere, that appears to be inconsistent with some of the observational constraints that we have for stars. And so this is sort of a question, but M-dwarf habitability is often posed as, planets around M-dwarfs, so it's horrible, they've got all kinds of nasty stuff happening, and maybe it's not so bad as everyone thinks. So I'll stop there and take questions. Thanks. So pretty much all stars that have an outer convection zone. Yeah, so the sun obviously flares. I showed you some nice movies. And we know that whenever you have an outer convection zone on the main sequence for stellar evolution, you're capable of generating magnetic fields, and X-ray emission and flaring is nearly ubiquitous on all those different kinds of stars.
I've been asked to remind you to repeat the question.
Oh, okay. All right.
Any other questions for Rachel?
So you showed us a lot of tantalizing but failing results in CMEs. Do you think there are, I'm aware of a few other attempts using blue shifts of lines and things after flares. Do you think there is any other promising observational avenue to find CMEs?
Yeah, so I think there are, and I mean, so the line of so the question was, are there any other tantalizing observational approaches that might be used that might get favorable results? So the reason why we went with this particular search of type 2 bursts was because it was a signature that was definitely produced from the CME and not the flare. And so the interpretation was simpler. So that was a big X. And I hope that this doesn't mean that no one else will ever try to detect a type 2 burst from another star ever. But I think it means that we need to turn to some of those other possible observational signatures that are going to be more thorny. But I think you can also, there's a hope of getting around that by appealing to big data, right? At this point, we've got a massive archive of 20 years of X-ray observations from both Chandra and XMM, and then numerous other high-energy satellites. So there's a potential there of maybe harnessing big data. If you've got a signature, if you've got one weird flare that you interpret as a CME, it's a weird flare. But if you've got thousands of flares and tens or hundreds of weird flares that are weird in the same way, then you're starting to make some progress. So I think that's one promising line of attack.
Could you use planets as a probe of CMEs via low-frequency emission from, say, a giant planet impacted by a CME or auroral emission, something like that?
Okay, so the question is, could you use planets as a probe of CMEs by looking at low-frequency emission? It's an interesting idea. However, in practice, it's really hard to even detect exoplanets at low frequencies. So, I mean, yeah, you can think of all kinds of geometries where you could have a planet and the CME is reflecting off the planet, and you're still going to work. You're still in the regime where you have to worry about whether your signal is going to be enough to be able to be detected.
Okay, then I have one.
Okay.
So how fits the likelihood is that that is the phenomenon versus there are CMEs, but you're just not detecting them?
Yeah, so that's a good question. So the question was how physically plausible is it that you could be having flares occurring without CMEs occurring? So I showed you a lot of evidence that on the sun, whenever there's a large solar flare, there's always a coronal mass ejection, except when there isn't. So there was an active region 2 or 3 years ago. It was one of the largest active regions that the sun's produced in recent history. And it produced this whole slew of very energetic flares, but no CMEs. And so the interpretation the solar physicists gave to that particular event was that there was a very large overlying magnetic field above the sunspot, and that was preventing the material from breaking out. So that is a plausible explanation for why you could have flares but no CMEs. I mentioned, I didn't stress a huge amount, but these are very active stars. They have large magnetic field strengths. We have not gotten to the point where we can make models of active region scale magnetic fields on stars, but that is a possible explanation, and it's at least consistent with the sort of 0th order, 1st order understanding of magnetic field geometries on stars. So it's not wild.
And that would be great for habitability, obviously.
Yeah.